Something great we can use a chi-squared test for is called a chi-squared test of homogeneity, which homo means same, geneity means geneity. Though the question you might want to answer here is, are two baseball players roughly the same? When I say roughly the same, I mean in terms of their records on strikes, balls, and hits. So we collect the data on these two players for quite a lot of pitches, and it's sort of tough to tell because the sample sizes are so different. But this sample size is roughly half of that, that's roughly half of that, and each of those is sort of roughly. Are they roughly the same, or is there a statistically significant difference between the two? So first you have your data, which we've collected here in this table. It works a lot better if it's in a table like this. To do the calculations, you're going to need to add up the total for each of these categories. Then you need to find the percent of the total in each category. So what you do is you say, okay, strikes were on total 700 out of 1346, balls were 492 out of 1346, and hits were 154 out of, you guessed it, 1346. So convert those into decimal 0.52, 0.366, 0.114. From there, you can come up with your expected counts using these numbers. So let's do that on a new sheet. For the expected counts, let's take this percent of the total and apply it to each player individually. So this player had 896 total pitches, assuming we're not allowing any other outcomes here where they were hit by a pitch or UFOs abducted them in the middle of the game. So take this 52% here and apply it to 896. So 0.52 times 896 gets you 466.0. Do the same thing here for the number of balls. Take 36.6%, multiply that by 896, and you get a total of 327.5. So do the same for the rest of these, and do the same for player 2. Use that 52% overall rate with the total for player 2. Now you can compare your observed to your expected. All your observed counts are up here in this table, so you can see most of them are pretty close. So you think these players might be roughly the same, but you don't know if it's statistically significant differences until you do the math. To come up with that, calculate for each entry in this table, comparing observed minus expected squared over expected. So in the first one, you have 450 as your observed, subtract 466.0, square that, divide it by, expected was 466. Same thing here, take your observed, 337, subtract your expected, 327.5, squared divided by expected. And then do the same thing for player 2. Before you move on, make sure you know how I got these numbers in the table. I'm not going to write down the formula for every one, but it works out to that. In practice, I should probably carry on more decimal points, but that's how many I had for this. For the test statistic, I just add those up, and I get my test statistic, chi-squared, is about equal to 3.7. My degrees of freedom is number of rows minus 1 times number of columns minus 1. So number of rows is 2, minus 1 is 1. Number of columns is 3, minus 1 is 2. So total degrees of freedom is 2. Now go use GeoGebra to find the p-value. Here I've gone to geogebra.org/probability or /classic #probability, and I've selected the chi-squared from the drop-down menu. Enter degrees of freedom is 2. I always want the upper tail for this test, and I enter the test statistic I just calculated. And here is my p-value, 0.1572. The p-value is 0.1572. Alpha is not given, so we'll assume 0.05. Now this p-value is greater than alpha, so we will fail to reject the null hypothesis. Except now you're probably thinking, wait a minute, what was the null hypothesis? The null hypothesis always works this way. Now here there aren't symbols because you're not talking about a proportion or a mean, so you just put it in words. The null hypothesis for a test of homogeneity is that the players have the same distributions. The alternate is that the distributions are not the same, and generally you should put at least one of those in context. Here I made it clear which distributions I'm talking about, so here I'm allowed to say they're not the same because I already said which one it is. So we failed to reject the null hypothesis. We didn't reject this, so we conclude that it's possible that these players are equally distributed, the same goodness, whatever. We don't conclude that the null hypothesis is true. We don't say they are the same. We just say they could be the same. What we're saying is our observed counts are consistent with this hypothesis. These are close enough to expected if they were both the same that we can say this is certainly possible.